Section 9.1, polar coordinates. We're going to start with some vocabulary here. This section is going to be very heavy on vocabulary. It's a lot of foundational information. The first vocabulary term here is polar coordinate system. It's a system of concentric circles, concentric meaning emanating from the same place and working our way outwards, and their center. Okay, the center of the graph, or the origin as we know it, is called the pole. Okay, and then the polar coordinate system has a polar axis. It's a horizontal ray directed from the right, or toward the right from the pole. Basically, it's the positive x-axis when we think of a graph. Okay, and we can plot what are called polar coordinates on our graph. Polar coordinates are ordered pairs in the form r comma theta, noting the distance and the angle the point makes with the polar axis. So this is an example. This picture right here is an example of the polar coordinate plane. Okay, you can see concentric circles, meaning they're just emanating from the center, getting farther and farther away, and we have angles as well. The polar axis would be the positive x-axis, starting at the center, starting at the origin, and working our way out to 0 degrees or 0 radians. Okay, what we're going to do first is we're going to graph polar coordinates. What we're going to do is how we're going to graph these is we're going to sketch the angle in standard position. So the initial side is going to be on the positive x-axis. The terminal side will rotate around that. And then we're going to go r units away from the pole on the terminal side of the angle. If our r value is negative, and I've got a couple of examples where it will be, you're going to go along the ray that is opposite the terminal side. So it's important that we have this grid where we see the lines going both directions, both out to the right and back to the left, because that's going to help us stay a little more organized. So let's try graphing a couple, and I gave you some polar graph paper, so grab that. If you want to cut it up and tape it into your notes like I did, that would be good. Otherwise, if you just want to keep a separate sheet, the 3-hole punch it and put it in a binder or something, and just label all of these examples a little differently. I do the normal 1, 2, 3, and when I get another set of examples or set of directions, then I renumber 1, 2, 3, but feel free to number however you want. Okay, so number one, we're going to graph here, 3, 60 degrees. So we're going to start with the terminal side of our angle, which is 60 degrees. Now my graph here is labeled in radians, but hopefully by now you're familiar enough with the degrees to radians that you know that 60 degrees is pi over 3. So I'm just going to draw a little bit of a dotted line, a dashed line right along pi over 3. So that's my terminal side, and now I'm just going to go 3 units out. So I'm going to do this in a different color, in blue. If you're going to do all of the graphs on one paper, on one polar sheet, that's fine too. You might want to just label these like A, B, C, something like that. 3 units out. So it looks like starting here at the center, go 1, 2, 3 units out on that red line, and this is our point right here. This is the point 3, 60 degrees, because this right here, from this line, the horizontal x-axis, or the positive x-axis, up to here, this is 60 degrees. Okay, let's try another one. Number 2, negative 1.5, 7 pi over 6. So now we're in radians, so we need to first draw our angle, and 7 pi over 6 is pretty convenient because we are on, we're describing our angle in radians. So I'm going to draw my positive x-axis. 7 pi over 6 is out here, and this right here, this angle. That's a really bad circle, so let's draw this. This is going to be right about in here. Actually, I'm going to do this. This isn't great, so we'll just try to keep it as tight as we can. This right here is 7 pi over 6 radians. Now, 1.5. So normally 1.5 would go out this way, but since it's negative, we're going to go back the opposite direction. So we're actually going to follow the pi over 6 line, which is this one over here. So I'm still going to draw this in blue, but 1.5 is going to be right in this general area. This right here is the point negative 1.5, 7 pi over 6. So if you're ever given a negative r value, a negative, think of it like a radius, we're going to go opposite the terminal side. So if the terminal side comes out into quadrant 3, we're going to go opposite back into quadrant 1. Or if it was down here in quadrant 4, then we go opposite back into quadrant 2. Let's try a third one here. Negative 4, negative 135 degrees. So this time we have negative angle measure, which is fine. Negative 135 degrees. So let's see, 90 degrees, negative 90 degrees would be down here. And then we're going to need to go another 45 degrees. Let's see, that's clockwise. So our negative 135 degrees is out here. So this right here, this length is negative 135 degrees, or that angle is negative 135 degrees. Now we need to go negative 4 units. If we were going to go 4 units, we would follow along this path again. But we're going negative, so we're going to need to go back 4 units the opposite direction, and we're going to go 4 units. So 1, 2, 3, 4 looks like about the one right inside the blue line. If you're looking at it, so it should be right there. Okay, this is the point negative 4, 135 degrees. Graphing, individual points, not terribly exciting, but what we can do with all of these points is we can make polar equations, and we can graph polar equations. We'll get into more polar equations in section 2. This is kind of an introduction to polar equations. Polar equations are equations expressed in terms of polar coordinates. Makes kind of sense. A couple of examples of polar equations. You could see something like r equals 2 sine of theta, because we know polar coordinates are r comma theta. Could also see something along the lines of r equals 3 minus 5 cosine of theta. Just a couple of examples there. We'll look at those graphs in section 9.2, but those are examples of polar equations, more basic ones, but not as basic as we're going to get here in section 1. What we can do and what we're going to do with these is we're going to graph them. Polar graph, set of all points whose coordinates r comma theta satisfy a polar equation. Like I said, we're going to look at the basic ones, the real basic ones here in section 9.1, and we'll look at the more advanced ones in section 9.2. So let's try a couple here. Graph the equation, r equals 5. So now this one doesn't say anything about our theta, our angle. So what this really says, it's all points that are 5 units away, that are 5 units away from the pole, or the pole again is the center or the origin. Okay, so let's come up with a few points. We don't necessarily have to make a table, but we can identify some points. We could say something like 5 comma 0. Doesn't say, our equation doesn't say anything about our angle, so we can have our angle be whatever. This just says our radius has to be 5, or our r value has to be 5. So we could have 5 0. We could have 5 comma pi over 4. We could have let's see, come up with a couple more here. 5 comma 7 pi over 6. We could have 5 comma, let's see, 19 pi over 12 if we wanted, 19 pi over 12, and so on. And we can just say, etc. Okay, so 5 comma 0 is right there. That's on the blue line in the middle of the circle. 5 comma pi over 4 is right there. 5 comma 7 pi over 6 is there. 19 pi over 12 is there. And it goes on forever. So pick a few more. We could have pi over 2. We could have 5 pi over 6, we could have pi, we could have 4 pi over 3, 11 pi over 6, something like that. The bottom line is, if we were to graph every point that had an r value of 5, what you would see, you wouldn't see a collection of points. If you step back from it, what you would see is a line. And we're going to connect all of these dots. So if we have an equation that says r is equal to 6. Really what we're coming up with is a circle with a radius of 6. Not a radius of 6, a radius of 5. If r is equal to 5, we're going to come up with a circle that has a radius of 5. It's 5 units. All of these points are 5 units away from the center. Okay, so anytime you're given r equals a number, you're going to end up with a circle. You might want to jot that down. Next equation is theta equals pi over 6. So now this one, it doesn't say anything about our r value. Our r value can be whatever we want, but it does say that our radius has to, or our angle has to be pi over 6. I'm going to slide this graph down just a touch. So, let's come up with some points. It doesn't matter what our r value is. We could be 1, and then our angle, our theta, has to be pi over 6. Pick another one. It could be 3, and then our angle would be pi over 6. We could have negative 2 with pi over 6. We could have negative 4 with pi over 6. You could have you could have a half with pi over 6, whatever you want. I'm going to put etc. here. Goes on forever. The list goes on forever, but our circle's not that big. So let's put some of these points on the graph. So 1 pi over 6 is, oh boy, that's really close to the center. That's like somewhere in there. And then 3 pi over 6 is right there. And negative 2 pi over 6, so pi over 6 we think about going this way, but again, if we're negative, we're going back the opposite direction. So negative 2 pi over 6 is going to be here, and then negative 4 pi over 6 would be here, and negative, let's see, 5, 6, negative 7 pi over 6 would be here, and 7 pi over 6 is there. And again, if we graphed every single point possible, what we would see is a line going through the origin, okay? So if you're given an R value, just an R value, you're going to come up with a circle. If you're given just an angle or just a theta, you're going to have a line going right through the circle, okay? Something to keep in mind as you graph a little bit here in section 9.1. The last thing in section 9.1 is the distance formula on a polar plane. So if I were to give you 2 points, let's say this point right here, and let's say this point right here. It's not on the graph, but we can make it work. Okay? How we're going to find the distance between them, so that would be this distance right there, is if P1, meaning R1, theta 1, and P2, R2, theta 2, are on the polar plane, then P1, P2, meaning the distance between them, is equal to this. And it's a big ugly square root. It's a long one, so just kind of give yourself plenty of room to write. And we're going to have a really long square root here. So this is equal to R1 squared plus R2 squared, and you'll get those from the ordered pairs that you're given, okay? And then we'll have minus 2 times R1 times R2 times the cosine of theta 2, I want to make sure I get that right, theta 2 minus theta 1. Okay, so we're going to basically, this part right here means, let me undo that, this part right here is just how far apart or how many degrees or radians the angles are from each other. So this is how far or how many degrees, let's change that, how many degrees slash radians apart the 2 points are. Okay, so I'll give you an example here of how to do this. So the distance between 2 points is equal to this whole big ugly mess. But this is something you can type into your calculator. So if you can identify what R1, R2, theta 1, and theta 2 are, it's really not that hard. It's just a matter of plugging it into the calculator. So for an example, while mapping out a level site, something that's flat, we're not worrying about hills or changing elevations, a surveyor identifies a landmark 450 feet away and 30 degrees to the left, and another landmark 600 feet away and 50 degrees to the right. What is the distance between the landmarks? So let's kind of draw a little picture here. So here's my person, here's my surveyor, and we're going to say we're looking out this way. So like we're looking out onto the positive x-axis. Let me draw my dashes a little bigger there. Okay, first landmark is 450 feet away, so let's say that this point right here is my landmark 1. We'll call this L1, and this distance right here is 450 feet away, and we make a 30-degree angle to my left. Okay, the second landmark is 600 feet away, so that's out here. This is landmark 2, and we are 600 feet away. Let me draw that in. 600 feet. These are both in feet. And we make a angle that is 50 degrees to the right. Now normally if we go counterclockwise, that's negative, so we'll just keep that in mind, negative 50 degrees. And the question is, what is this length? What is the length I just drew in blue? And we're going to use this formula to help us find that. Okay, so we can say L1, if we think about it in terms of polar coordinates, our R value is 450, and our theta is 30 degrees. Okay, L2 is 600 feet away, 600, and our degree measure is negative 50. So we have our 2 points. We have R1 theta 1 and we have R2 theta 2. Now it's just a matter of putting it into the calculator. Let's figure out what we should type into the calculator before we actually do it. Okay, so we'll do this in blue. So we're going to say that L1, L2 is equal to big square root, leave yourself plenty of room. Our first radius we'll call landmark 1, so that's 450. So 450 squared plus second radius squared, so 600 squared, minus 2 times R1, 450 again, times R2, which is 600 again, 600, times the cosine of our two angles. Now, it really doesn't matter what order you subtract them in. Usually, well, I guess in my notes I did 30 minus -50, but in the formula here, it should do probably -50 minus 30. Either way, the cosine is going to be the same. So it doesn't really matter which way you do this. I'm going to go with what I had in my notes, 30 minus -50. 30 minus -50. And we're going to type all that into our calculator. Now, if you want to make this 80 before you type it in, feel free. What you're going to find after you do all this is that this is approximately 684.6 feet, or we could say, you know, about 685 feet apart. So this distance right here, 685 feet between the two landmarks.